In these next few examples, we're going to determine how to solve for the term or the time period of a compounded interest investment. Example 1. An investment of $45,000 earned $20,028.44 in interest at a rate of 12% compounded monthly. Determine how long the funds were invested. Let's begin by taking a close look at the information that we know. We know that we have an investment of $45,000, so that's going to be our present value. Present value is $45,000. And we've earned $20,028.44 in interest. So over this particular time period, I've earned interest of $20,028.44, so that I have a maturity value then of the principal plus the interest. Now, that means that I'm going to take the $45,000 and add the $20,000 in interest. That's going to give me a maturity value at the end of the term of my investment of a total of $65,028.44. The problem is I don't know what the time period is. N is not known. But I do happen to know that the interest rate is 12% compounded monthly. So at a rate of 12% compounded monthly, I know that the interest rate is 12% divided by 12 months per year, or 1% per month. You will note that I always make a note of how the interest is compounded or calculated. That's very critical. And so, if my focal date then is set for the time in the future, I'm going to use the formula S is equal to P multiplied by the compound interest factor 1 plus I to the exponent n. I'm going to substitute the known values and work this out. So I'm going to have 65,028.44 is equal to the principal of $45,000 multiplied by the compound interest factor of 1 plus 0.01 per month raised to the power of n. And n is number of months. I'm going to solve for n by starting off by dividing both sides by 45,000. So I'm going to have a new equation that says 65,028.44 divided by 45,000 is equal to 1.01 to the exponent n. Working this out on your calculator, you'll end up with 1.445 and a whole bunch of other stuff is equal to 1.01 to the exponent n. Now this equation is called an exponential equation because the variable n is up in the exponent. The only way that you can solve an exponential equation is using logs. We can use logs base 10 or natural logs. We can log both sides or ln both sides. What we'll do is we'll take the ln operator of both sides of this equation, and that will bring down the exponent using the properties of logarithms. So we'll have a new equation that says that the ln of 1.445 and whatever else you have is equal to the ln of 1.01 raised to the exponent n. Now, one of the properties of logs or lns is that the exponent can come out and become a factor or a multiplier. So the ln of 1.445, etc. is equal to n times the ln of 1.01. So what that means now is that we can divide both sides by the ln of 1.01 to solve for n. So n is going to equal to the ln of 1.445, etc., divided by the ln of 1.01. Working this out on your calculator, you will obtain a value of n is equal to 36.99, or approximately 37, and that works out to 37 monthly periods. So our final conclusion is that n is equal to 37 monthly periods. That's a little bit more than 3 years. In fact, it's 3 years and 1 month. So the term or the time for this investment is 3 years and 1 month. Example 2. How much time is required for an investment to double in value at a rate of 9% compounded semi-annually. Let's once again start off with a time diagram. So we don't know how much time is involved, so I'll have a time diagram that goes from 0 to n periods. And we have an interest rate of 9% compounded semi-annually, so I'm going to make a note of that. 9% compounded semi-annually means that I'm going to divide by 2 periods per year to get the interest rate. And the interest rate now is 4.5% per 6 months. Now we want the investment to double in value, and I don't know what the amount of the investment is, so it's pretty arbitrary what we choose. So let's choose a nice simple amount of $100. $100 after a certain time period, we wish to have it doubled in value, so that means that the maturity value is going to be $200. It's quite irrelevant what number you use as long as you double the investment. So now I'm going to set up my compound interest formula that says sum is equal to principal multiplied by 1 plus I to the exponent n. My focal date is the date in the future. That sum is $200, and that's equal to the principal of $100 multiplied by 1 plus the 0.045 raised to the exponent n. N in this case is going to be the number of semi-annual periods because the interest rate is compounded semi-annually. So now I'm going to attack this exponential equation by dividing both sides by 100, and I'm going to have 200 divided by 100, which is equal to 2, and that's going to equal to 1.045 raised to the exponent n. Where does the 2 come from? The 2 comes from the fact that the maturity value is 2 times the principal. So doubled in value means that the S divided by P is going to be a ratio of 2 to 1. We're going to now take the ln of both sides, so we're going to have ln of 2 is equal to the ln of 1.045 raised to the exponent n. So the ln of 2 is now equal to n times the ln of 1.045. I'm going to divide both sides by that factor of ln of 1.045, and we'll end up with an isolated value for equation for n. N is going to be equal to the ln of 2 divided by the ln of 1.045. Working this out on our calculators, we'll end up with an approximate value of 15.747. So n is going to be equal to 15.747 semi-annual periods. Now, we're not going to use a value of 15.747. It probably makes more sense to use full semi-annual periods. So I'm going to say that we need at least 16 semi-annual periods because 15 semi-annual periods is not going to cut it. It's going to be a little bit short. So we're going to conclude by saying that we need at least 16 semi-annual periods or 8 years in order to double our money. In fact, we'll have a little bit more than double our value. Certainly if we used 15 semi-annual periods, we'll have a little bit less than double the value. And you can check that and confirm that by substituting into the original formula. So our conclusion is that we'll need at least 8 years to double our money at that particular rate of 9% compounded semi-annually.